Okay, hello Math Counts friends. In today's video we're going to be taking a look at probability and combinatorics. I had a request to do a video on this material and I hope you guys will enjoy it. It's some great material that comes in really handy because there are a lot of the Math Counts problems you'll find that are probability and combinatorics related. So let's jump right in. The first thing I want to talk about is just basic probability. So if you have a series of events that can happen. So let's say there are 3 events that can happen, A, B, and C, and you're asked what is the probability of getting event B. If they're equal probabilities, these 3 things are equally likely, then the probability is just 1/3 because it's 1 out of the 3 possibilities. B is just 1 of the 3 possibilities. So a lot of times in probability problems, you need to figure out how many possible events there are, and then in some cases you need to figure out how many of them satisfy the criteria to be a successful event. So in this case, a success would be only B, and there are 3 equally likely events. The probability would be 1/3. Now, one thing that can happen is they can ask you what's the probability of B or C. So the probability of B, we'll just write it like that, P of B. The probability of B we said is 1/3, and the probability of C is 1/3. And as long as B and C can't happen at the same time, meaning that they're mutually exclusive, the probability of B or C, maybe I'll write it as B or C, is just going to be the sum of the probability of B. Yeah, maybe actually I'll just write it the normal way that you're used to seeing it. Probability of B or C is going to be equal to the probability of B plus the probability of C. So in this case, it would be 1/3 plus 1/3, which would be 2/3. But this only works if B and C are mutually exclusive. Okay, so that's an important concept. They have to be mutually exclusive, meaning that if either one of them happens, the other one can't happen. So let me give you an example. If you roll a die, you can get a 3 or you can get a 4. You can't get a 3 and a 4 at the same time when you roll a die. So those are mutually exclusive events. But if you said, for example, the probability of getting your die roll to be greater than 4 is going to be 1/3 because only 5 and 6 are greater than 4. And then you could also say the probability of getting the die roll being even, that would be 1/2 because half of the numbers on a regular 6-sided die are even. And so, but these are not mutually exclusive. You can have both of these at the same time. If you get a 6, it's greater than 4 and it's even. So if someone was to ask you what's the probability that you'll get when you roll a die it'll be greater than 4 or it will be even, you can't just add these 2 probabilities because these 2 events are not mutually exclusive. So hopefully that makes some sense. Yeah, okay, so let's move on. I think we've covered the basic probability concepts here. Let's move on to something a little bit more tricky. And that is the idea of independent events. So there's this important concept of independent events. Okay, so what would make something an independent event? If one event does not depend on another event. So for example, if I said, so Sam and Ellie each have a 1/3 chance of getting an A on their math test. And then I ask what is the probability that they both get an A on their math test, right? So you would say the probability that Sam gets an A is 1/3, And the probability that Ellie gets an A, Ellie gets an A is also 1/3. And if those events are independent, then the probability that they both get an A, so this is probability that Sam and Ellie both get an A, would be the product of these two probabilities. So 1/3 times 1/3, which would be 1/9. Now, there might be some reason why they were dependent on each other. So for example, if the test was really easy, that might, if the test happened to be easy, maybe 1 out of every 3 tests is easy and they both get an A on all the easy tests, then these two probabilities would be sort of linked together. And whenever there was an easy test, they would both get an A at the same time. And so that would make them dependent. But if it's really just the test is always the same difficulty and Sam and Ellie sometimes study hard, and whether they study hard or not, whether Sam studies hard or not doesn't depend on whether Ellie studies hard or not. For example, they're not in a study group together or something like that. It'll just be completely random and independent events between Sam and Ellie. So it's important to understand whether events are independent, because if they are, you can multiply the two probabilities to find the probability of both things happening. So I like to think about that sometimes geometrically as well. Let me just draw what that would look like. So for example, I think of like a probability space when there are two different events. I think of a probability space as being a two-dimensional structure, like for example a rectangle or a square. So I have the probability of Sam getting an A in this direction along the x-axis, and the probability of Ellie getting an A on the y-axis. And 1/3 of the time, Ellie will get an A. So that's this top third here. And the other 2/3 of the time, she doesn't get an A. And then the same thing for Sam. I can split Sam's score up into 3 sections, and the top third of Sam's, he gets an A, right? So this is 1/3 of the time Sam gets an A, 1/3 of the time Ellie gets an A. And maybe just to separate those, just to make that clear, this might be the 1/3 where Sam gets an A, right? And this might be the 1/3 where Ellie gets an A. And what's the probability that they both get an A? Well, it's when where those two overlap. So that would be this part here, and you can see that it's 1/9 because it's 1/3 times 1/3. So if if Sam and Ellie studied together, and sometimes they studied and sometimes they didn't, then this probability space might look different. It might, there might be something like this. Let's see. So it might look like, let's say 1/3 of the time Sam gets an A. So this is still Sam over here, but we might have something like, let's see if I can make this. I guess we can't draw it as a rectangle anymore because there's going to be a small probability of one of them getting an A when the other one doesn't. Let's say like this. So this might be Sam but not Ellie, and this might be Ellie but not Sam, and then this is Sam and Ellie, and this is neither one getting an A. So they might still each have 1/3 of a chance. Like for example, Ellie's third would be this shape here, and Sam's would be this third here. But since they're no longer independent, we can't just draw this grid like this with these straight lines, because you can see that if Sam gets an A, Ellie is more likely to get an A. If Sam doesn't get an A, like Sam gets a B or a C, then Ellie is more likely to get a B or a C. And less likely to get an A. So, okay, hopefully that made some sense. let's go on to another concept. So that's independent events. When you have independent events, you can multiply the probabilities. Let's talk about something else. So let's talk about conditional probabilities. So let's see. Oops. So a conditional probability is could be, for example, the probability that Sam gets an A given the fact that Ellie got an A. So we write it like that. The probability that Sam succeeds given the fact that Ellie succeeds or gets an A. And that is equal to the probability that Sam and Ellie both get an A. Sam and Ellie both get an A divided by the probability that Ellie gets an A. So let me give you an example. Let's make a Venn diagram where you have something like this. So let's say Sam and Ellie take 100 tests, and let's say that the tests that are inside this circle are ones where Sam gets an A, and the tests that are inside this circle are the ones where Ellie gets an A. Right? So let's say they take 100 tests, and let's say in 65 of them, neither one gets an A, and in 10 of them, maybe Ellie gets an A, but not Sam, and then let's say that in another 12 tests, they both get an A, and then what have we got left? So 87, so there's 13 more where Sam gets an A, but Ellie doesn't. So here, the probability of Sam getting an A given Ellie gets an A is the probability of Sam and Ellie. That's this probability here, which would be 12 out of 100. So that's 12 out of 100. And then we would divide by the probability of Ellie getting an A. That is 22 out of 100, right? So 22 out of 100. So this conditional probability of Sam getting an A given the fact that Ellie gets an A would be 12 divided by 22, or that would be 6 over 11 if we simplify it to the common fraction. So yeah, so that's what a conditional probability is. Sometimes that comes in handy. Another thing that comes in handy sometimes is the concept of expected value. So sometimes it's kind of rare, but sometimes they'll ask, what is the expected value of a number? So, for example, if you had a die, let's just start with a fair die, where it's a 6-sided die. So you can get a 1, you can get a 2, you can get a 3, you can get a 4, you can get a 5, and you can get a 6. And let's say all of these are equally likely. They might ask you, what is the expected value of the number that you roll on a die? And it's a little, that terminology is a little strange, because the expected value doesn't mean the value that you actually expect. It's kind of the average, or it's actually a weighted average value. But in this case, it's just an average, because these outcomes are all equally likely. So there's a 1/6 chance that you'll get a 1, there's a 1/6 chance that you'll get a 2, and so on, 1/6 chance for each one. And in order to compute the expected value, expected value, I'm just going to abbreviate it as val, that's going to be equal to the probability of getting the first one times 1, the probability of getting a 1 times 1, plus the probability of getting a 2 times 2, plus the probability of getting a 3 times 3, and so on, all the way up to probability of getting a 6 times 6. So if we compute that out, that's going to be, these probabilities are all 1/6. So we can take that out as being 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. And you might recognize that this is just the average, right? When you take the average of 6 numbers, you just add them all up and divide by how many numbers there are. And the expected value, if you have equally likely, if all the numbers are equally likely, then the expected value is just the average. So in this case, it'll be 3.5. 3.5 would be the expected value. Now, it's impossible to roll a 3.5 on a die, right? So that's not the value we really expect. But the expected value is kind of the value that is kind of the average value, or the value that on average is going to be closest to what you expect to get. In other words, yeah, it's you can also think of it as the it's most likely that your value is going to be close to that. So so if you had an unfair die, where, for example, instead of 1/6 probability, you had 1/8 probability of all the numbers from 1 up to 5, so that would be 5/8, and then you had a 3/8 probability for 6, then you would get your expected value would be a little different. You would have 1/8. This would be 1/8 times 1 plus 2 plus 3 plus 4 plus 5 plus 3 times 6, because this is 3/8, so there's a 3 in here. And then, you would get a value that would be a bit higher, right? So this is 18 plus 9 is 27, 30, 33, so it'd be 33 over 8, which is, yeah, quite a bit higher. That's a little bit more than 4, right? So it's 4 and 1/8 if you put it as a mixed number. So it's the expected value has gone up because the 6 is more likely. So yeah, that's a concept that might come in handy, the concept of expected value. All right, let's move on to the next concept. And the next thing I want to talk about is how many different ways you can do things. And a lot of times that's really useful when you're computing probabilities. So for example, let's say I want to make an outfit and I have 3 shirts and I have 6 hats and I have 2 pairs of pants. And I asked the question, well, how many different outfits can I make? And there's a lot of different ways to think about it, but one thing I like to do is I like to draw a little diagram. So let's say I put my 3 shirts here, 1, 2, 3. Those are my 3 shirts. And then I put my 6 hats here. So 1, 2, 3, 4, 5, 6. Those are my 6 hats. And then my 2 pairs of pants could be down here, 1, 2. So each outfit would be some sort of connect the dots between one of these 3, one of these 6, and one of these 2. So let me just do one example here. I could take this shirt, this hat, and this pair of pants. That would be one outfit. And if I were to try to count all these, it would be a lot. And you might get lost trying to count them all. But fortunately, there are some nice tricks here. So for example, if you just think about it, let's just look at the shirt. Let's just look at the shirts and the pants. Let's forget about the hats for a minute. So if I just had shirts and pants, I would say I could take this shirt with either pair of pants, this one or this one. That's 2. And then I could take this shirt with either pair of pants. That's another 2. And then I could take this shirt with either pair of pants. That's another 2. So altogether I've got 2 plus 2, 2 plus 2 plus 2, which is 6 altogether, right? So, and you might realize that what I did really was just multiply the number of shirts by the number of pants, because for each shirt I could do any pair of pants, and so it was just multiplying. Now I could do the same thing with shirts and hats, right? There would be 6. I would get 6 with this shirt, 6 with this shirt, 6 with this shirt. So there would be, if I just had shirts and hats, it would be 3 times 6 instead of 2 times 6. Or sorry, 3 times 6 instead of 3 times 2. So that would be 18. And then now for each, let's go back to, let's draw all those 18. So I've got these 2, or no, sorry, these 6, all those guys, and then I've got all 6 of these. 1, 2, 3, 4, 5, 6, and then I've got all 6 of these, right? 1, 2, 3, 4, 5, 6. So altogether I've got 18 outfits so far, just with shirts and hats. And now, if I picked the first pair of pants with all those, I could just connect all these down here. That would still be 18 outfits, just with that pair of pants. So there's 18 outfits that you can get with this pair of pants, but then I could do all 18 of those outfits with this pair of pants instead. That would give me another 18, right? So altogether, so really I'm multiplying by 2 by having these pants. So really it's just, you just multiply the number of shirts times the number of hats times the number of pants. So you multiply them all together, and this is 18 times 2, this is 36 outfits that I could have. Now this is also useful, like for example, if they say how many different combinations can you make on a combination lock with 4 digits. So each digit is 0 to 9. That's 10 possibilities for the first digit, 10 possibilities for the second digit, 10 possibilities for the third digit, 10 possibilities for the fourth digit. You would multiply those all together and you would get 10,000. Which makes sense because the combinations, if you have a 4-digit combination lock, the first one you could have would be 0, 0, 0, 0, and the last one you could have would be 9, 9, 9, 9. And there are 10,000 numbers, including the first and the last one here. If you just counted from 1 up to 9999, that would be 9,999, but you've also got 0, 0, 0, 0, so that's a total of 10,000. So that, hopefully that just makes intuitive sense there. All right, great. So the next thing that happens sometimes is they ask you, for example, let's say I take my 6 hats and I want to arrange them on my shelf. And they ask, how many different ways can I arrange those 6 hats on my shelf? So again, you can multiply the different possibilities. So you have these 6 spots, 1, 2, 3, 4, 5, 6 spots on your shelf. So here's your shelf, and you can put them in any order you want. So you've got, let's say you've got your hats are named A, B, C, D, E, and F. Those are your 6 hats, and you can pick any one of these to put in the first spot, right? So you could pick D, for example, to be the first one. And since there are 6 possibilities there, you can put a 6 here. But once you've selected D, and you're looking at the next spot on your shelf, and you're saying, how many possibilities are there for this one? Well, once you've selected one of these, there's only now 5 remaining possibilities. It's either A, B, C, E, or F. And it doesn't matter which one I picked. If I had picked B instead of D, there would still only be 5 possibilities, because one of them would have been taken. So basically, if I want to pick 2 hats to put on my shelf, the number of possibilities is 6 times 5, because I could pick any of the 6 for the first one, and then I could only pick any of the remaining 5 for the second one. So that would be 30 possibilities to arrange 2 hats on my shelf. But if I wanted to arrange all 6, there would be 6 possibilities here, 5 here. Then once I pick those 2, there's only 4 possibilities for that one here, 3, 2, and then once you pick, say you've gone and you've picked all the hats on the first 5 slots, there's only 1 left. So it's just 1, and you multiply these all together, and this number, 6 times 5 times 4 times 3 times 2 times 1, there's a special name for this when you're multiplying a bunch of numbers, a bunch of integers going down to 1. So this is called 6 factorial. We write it like this, a 6 with an exclamation point. 6 factorial just means 6 times 5 times 4 times 3 times 2 times 1. And it's good to memorize probably all the factorials up to 7 for math counts. So for example, 0 factorial is 1. That's a little weird to think about because you're not multiplying any numbers together when you do 0 factorial. 1 factorial is just 1 times, times nothing, so it's just 1. And then 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. And if you keep going, 6. If you keep going, 4 factorial is going to be 24. 5 factorial, 4 factorial, 5 factorial is 120. And then 6 factorial is 720. So, and then 7 factorial, if you want to memorize that one, is 5040. So yeah. All right, so those are useful. Those factorials are useful because they come in handy in probability combinatorics problems. So this is kind of combinatorics, finding out how many ways you can do something. That's what we call combinatorics. But how many ways can you arrange 6 hats on a shelf? 6 factorial, 720. So that's called. There's a fancy word for that. It's called permutations. Permutations is how many ways can you arrange some items that are all different. Those are called permutations. So, all right. Yeah, let's move on to combinations. So permutations. Well, let me write formally the equation for permutations. Permutations. The thing you need to remember here is that if you have n items and you want to know how many ways you can permute m of them, we write that npm like that. So in other words, so for example, if I had, you could have 6p3, that would be how many ways can I arrange 3 of my 6 hats on a shelf. So npm would be n factorial divided by let's see, divided by n minus m factorial. Okay, so in this case, 6 hats, and I want to put 3 of them on my shelf. That would be 6 factorial divided by 6 minus 3 factorial, which would be equal to 6 times 5 times 4 times 3 times 2 times 1, all divided by, this is going to be 3 factorial, so 3 times 2 times 1, and you always get these first ones canceling out like this. And it's just 6 times 5 times 4. So yeah, that's how you do permutations. If there was only 1 hat on the shelf, this would be 6 permute 1, which would be 6 factorial divided by 6 minus 1 quantity factorial, which is 5 factorial, right? So this is 6 times 5 times 4 times 3 times 2 times 1, all divided by 5 times 4 times 3 times 2 times 1. These all cancel out, and you're just left with 6. That's like a kind of a hard way to do a very simple problem, because you could just think about that. How many ways can I arrange, you know, if I have 1 slot and I have 6 hats, how many choices do I have? It's only 6, right? There's just 6 choices. But anyway, that's kind of the formal way to do it. So, and it comes in handy when the numbers are not so simple. So the next idea is combinations. So let's go into combinations. So combinations is very similar to permutations, except the order doesn't matter. So here, like, let's say I have my 6 hats, for example, but I am going to choose 4 of them to give to my friend. Right, so that would be 6 choose 4. So this is called combinations. Combinations. And if I had 6 hats, I'm going to choose 4 of them to give to my friend. My friend doesn't care what order they're in. I'm not going to give them to him in any particular order. I'm just going to choose 4 of them and give them to my friend. And the question is, how many different ways can I choose those 4? And so that is going to be equal to 6 factorial divided by 6 minus 4 factorial. So far it's the same as permutations, but I also divide by 4 factorial. Yeah, so let's think about this for just a minute. If I was putting them in order, I would have 6 choices for the first one times 5 choices for the second one, times 4 choices for the third one, times 3 choices for, let's see, this was the first one, second one, third one, so 3 choices for the fourth one. But if the order doesn't matter, then, you know, if I chose D, E, A, C, that would be the same thing as choosing C, A, E, D, or C, E, D, A. And so all of these would be the same. And how many of these are there? How many different ways can I order these for? Well, there's 24 of them because there's 4 times 3 times 2 times 1. So this number is too big because it has a bunch of duplicates. And so I need to divide by how many of them are, in each, so if I were to list out all these 6 times 5 times 4 times 3 permutations, they would include 24 that had these 4 letters in them, and then another 24 that had another 4 letters, and another 24, and so on. But there would be a bunch of sets of 24. And so I would need to divide by 24 to get the number of combinations. So here, that's why I'm dividing by 4 factorial. So this would equal 6 times 5 times 4 times 3 times 2 times 1 divided by 6 minus 4 factorial is 2 times 1, and then the 4 factorial, 4 times 3 times 2 times 1. And you're always going to cancel these ones out, and then you've just left with 30 over 2, which is 15. So there are 15 combinations. There are 15 possible ways to choose those 4 hats that I'm going to give to my friend. You could think of it maybe a little more simple that, you know, by choosing 2 to not give to my friend, that's the same thing as choosing 2 to give to my friend, right? And that might be a little bit easier to think about. Like I could choose, I have 6 choices for the first one that I'm not going to give to my friend, and then I have 5 choices for the other one that I'm not going to give to my friend. So this would be 30 possibilities, but the thing is, it's the same to choose C then A as it is to choose A then C. And it's also with any other pair, right? DE is the same as ED. And, you know, FB is the same as BF. So if I have these 30 possibilities, they're going to be in pairs like this. And so how many pairs are there going to be? Well, there's going to be 15, because if there's 30 altogether and they're all in pairs, there must be 15 pairs. So that's, again, the same thing. I'm doing 6 times 5 divided by 2. So there are 15 possibilities there. Okay, so that's combinations. Okay, so I think I've gone over like a lot of the basic concepts now. I do want to go over a couple other more advanced concepts. So, for example, let's say that you were asked how many unique ways are there to arrange the letters in the word balloon, right? So BALOON. Okay, so if all the letters were different, the number of ways to arrange this would just be 6 factorial. 6 factorial. But since you have 2 O's that are the same, these 6 factorial ordering, some of them are going to be the same. Because if you number this one as O1 and O2, if those O's are indistinguishable, you know, then this balloon is the same as, you know, O2, O1. And, right, these two will be the same if these two are indistinguishable. I'm just writing a subscript on them so that we can tell the difference. But if those 2 O's are the same, you know, if we switch their positions, no one will be able to tell the difference, right? So you have to divide by 2 factorial. If there were 3 O's, like if it was BAOOON, and you want to know how many orderings, there are 6 different orderings of these 3 O's that are indistinguishable because there are 3 factorial. So there we would be dividing by 3 factorial to get the number of orderings. And the same is true if you had another. Let's think of a word that has 2 double letters, right? Let's see. Well, let's see. Well, okay. So let's say you had a word that had two O's and 3 E's. I'm not going to think of one, but and then it had some other letters, right, like an R and a B or whatever. So altogether, the number of letters is 1, 2, 3, 4, 5, 6, 7. So you'd have 7 factorial orderings, but then you have to divide by 2 factorial because there's 2 O's. And you also have to divide by 3 factorial because there's 3 E's. So this would be the number of different orderings of these letters that are unique. So hopefully that makes sense. Another thing that is handy is what we call stars and bars. So there are some problems where they might ask, for example, well, let's say that I have 7 pencils and I want to give them to my 4 friends. So I have 7 pencils and I want to give them to my 4 friends. And I want to know how many different options do I have to distribute them to those 4 friends. So my 4 friends might be Albert and Bill and Carl and David. So, for example, I could give Albert all 7, right? And then Bill would get nothing. Carl would get nothing. David would get nothing. That's one option, right? There are a lot of possibilities here. And so what's handy here is to find a way to represent these with some symbols in order, some ordered symbols. So for example, I could represent this situation where Albert gets all 7 pencils by putting a star, 7 stars in a row. 1, 2, 3, 4, 5, 6, 7. Those are my 7 pencils. And then 3 bars. Okay, so what this represents is that any stars that are on this side of this first bar, those are Albert's. Any stars, those are Albert's pencils. Any stars that are in between these 2 bars are Bob's. Any stars that are in between these 2 bars are Carl's, and any stars that are over here are David's. And so this ordering of stars and bars represents this situation where Albert gets all the pencils. And there's a one-to-one mapping between the ways that you can order these stars and bars and the ways that you can distribute your pencils. So, for example, if I just took another random pattern like star, and I've got to have 7 stars and 3 bars. So I might say star, star, bar, star, bar, star, 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 bar, star. I've got 7 stars, 1, 2, 3, 4, 5, 6, 7, and 3 bars, 1, 2, 3. So can you tell from this representation how many pencils each of my friends got? Yeah, you can. You can see that Albert got 2, and Bob got 1, and Carl got 3, and David got 1. So this is something we can solve. It was really hard to think about how many different ways I can distribute 7 pencils to my 4 friends, but if I can link it with this list of stars and bars, then I can figure it out using what we've just talked about. So the number of stars you have is equal to the number of pencils, and the number of bars you have is 1 less than the number of friends, because you can see you need 1 less separator than the number of friends you have. So in this case, we have 7 stars and 3 bars. That gives us 10 altogether, so that's 10 factorial ways to arrange these. But since the stars are all identical, in other words, my pencils are all identical, let's say. I don't have like a red pencil and a green pencil. It's just, I'm just giving out a number of pencils. It doesn't matter which one goes to which friend. So that means I can divide by 7 factorial. And then because the bars are all identical, I can divide by 3 factorial. And so this would be my answer. If I multiply that out, I'll get 10 times 9 times 8. And then I don't need the times 7 all the way down because that'll all cancel with the 7 factorial. And then that's going to be divided by 6, which is 3 factorial. And let's see, I can cancel this out. It'll give me 3, 2. I can cancel this, it'll give me 5. So it's 15 times 8. So that'll be, let's see, 120, I believe. Yeah, 15 times 8, that'll be 4 times 30, yeah. So 120 would be the number of ways that I can distribute 7 pencils to my 4 friends. So hopefully you understand that thing stars and bars, because it comes in really handy in some of these combinatorics problems. Okay. All right, now I want to actually solve some problems. We've done enough learning for now, so let's jump into some problems. So this first problem is a very easy one. It says if a marble is chosen from a bag that contains 10 red marbles, 5 blue marbles, and 15 white marbles, let's see. What is the probability that the marble chosen is blue or red? Okay, so blue or red, there's 5 blue and there's 10 red. So the number of ways it can be blue or red is 15. And the total number of ways is the total number of marbles you have, which is 5 plus 10 plus 15. And this just gives us 15 over 30. And importantly, it says express your answer as a common fraction, which means that we have to simplify this and get rid of any common factors here. And it gets just to be 1/2. So, all right. So let's move on to the next one. So this one says, this one's also very easy. A bag contains 3 white, 4 blue, and 5 red marbles. What is the probability that a marble selected at random is blue? So again, you just say the number that's blue is 4 divided by the total number, which is 3 plus 4 plus 5. And the probability is just going to be 4 divided by 12, which is just 1/3. Okay, very good. Let's see if we can get a harder one. So this one says a container has 10 green discs, 10 white discs, and 10 red discs. If the discs are randomly selected from the container without replacement, what is the minimum number of discs that must be drawn to be certain that 3 discs of the same color have been selected? So sometimes they'll give you a problem that's kind of like this. Like they'll say like you have 7 pairs of socks in your drawer and your room is dark. You can't tell if you've got a match. How many socks do you have to draw out of your drawer in order to ensure you have a match? So the way to think about it is you can draw 1 of each pair. That'll be 7 socks. And maybe you won't get a match because you might have 1 of each. So if you draw 7, you're not guaranteed to get a match. But as soon as you draw that 8th one, it has to match 1 of those 7. It's very similar here. If you want to be sure that you get at least 3 discs of the same color, you can think that you could draw a green and a green, and then a white and a white, and then a red and a red. That's 6 things that you could have drawn without getting 3 of the same color. But now you can't draw any more. As soon as you draw that 7th one, it's got to be either green or white or red. So you're going to have 3 of the same color. So the answer here is 7. All right, let's take a look at the next one here. So this one says, how many different arrangements of the 6 letters of the word yellow can be made if the first letter must be W and the last letter must be L? Okay, so you've got this number of arrangements. We know how to do this. We just learned. So let's see, I've got my 6 spots here. It says the first letter has to be W and the last letter has to be L. And so what's left? Well, what's left is Y, E, there's still another L, and then there's an O. So these 4 letters have to be put into these 4 spots. Excuse me. And the question is, How many ways can you do that? Well, all these letters are different, so this is just going to be 4 factorial. We had 2 L's, but one of the L's was fixed into this spot, and so we don't need to worry about that duplicate, because the ones that are left that we can move around is just these 4, and they're all different. So there's 4 possibilities for what goes in here. Once we pick that one, there's going to be 3 possibilities here, and then 2 possibilities here, and just whatever's left goes here. So there's going to be 4 factorial, which is 24. So that's going to be the answer to this one. All right, let's take a look at this one. When 4 fair coins are tossed, what is the probability that the outcome will consist of 2 heads and 2 tails? Okay, so here it's useful to know the combinations formula, because basically there's a lot of different possibilities when you toss 4 coins for what happens. If you think about it, there's 2 possibilities for what the first coin could be, there's 2 possibilities for what the second coin could be, 2 possibilities for the third coin, and 2 possibilities for the fourth coin, and you multiply those all together to get the total number of possibilities, which is 16. But how many of those are going to have 2 heads and 2 tails? I mean, obviously if you have 2 heads, you're going to have 2 tails. So there's going to be some number of these 16 that have 0 heads, some number that have 1 head, some number that have 2 heads, some number that have 3 heads, and some number that have 4 heads. And the way to figure that out is to think, how many ways can I choose 2 of these 4 spots to be heads? So that is 4 choose 2. And we have a formula for 4 choose 2. And by the way, I should have mentioned that 4 choose 2 is sometimes also written like this. You put parentheses and you put a 2 and a 4 like this. So this is 4 choose 2. And that is equal to 4 factorial divided by 4 minus 2 factorial, which is just 2 factorial, and then another 2 factorial. So this is going to be 4 times 3 divided by 2, which is just going to be 6. So there's 6 ways to get 2 heads, and there's 16 total ways. So the probability is going to be the ratio of these two. It's going to be the number of ways you can get 2 heads divided by the total number of ways. So it's going to be 6 divided by 16, which is also when you simplify it, that's 3 over 8. So the answer there is 3/8. Okay, let's take a look at the next one. So this says 3/4 of the students in Mr. Shearer's class have brown hair, and 6/7 of his students are right-handed. If Mr. Shearer's class has 28 students, what is the smallest possible number of students that could be both right-handed and have brown hair? So sometimes I think it might be useful to do a Venn diagram here. Let's say that this color circle is, let's say this is the ones that have brown hair. Brown hair. And then let's say that this circle is the ones that have that are right-handed. So this is right-handed. And it says 3/4 of the students have brown hair. So the total number of students that have brown hair, I mean, there's 28 students altogether. So 3/4 of 28 is going to be 21. So brown hair, there's going to be 21 total inside this circle. And then inside the other circle, we're going to have 6/7 of the students, so that'll be 24. So there'll be 24 inside this circle. And the question is, what's the smallest possible number of students that could be both right-handed and have brown hair? So they want to know the smallest number that could be in this area here. And the thing is, there's 4 numbers. There's this number A here, this number B here, C here, and then D here outside. And we know that 24 is going to be B plus C, and we know that 21 is going to be equal to A plus B, and we know that 28 is A plus B plus C plus D. It's going to be 28. So hopefully you can see that the way to make B as small as possible is to make D let's see, to make D as big as possible. Is that right? Was the smallest possible number of students that could be both right-handed and have brown hair? Yeah. So, so one thing you can see is that 21 plus 24 is equal to A plus 2B plus C. And so that's equal to 45. And then if we subtract these two equations, we get D minus B is negative, let's see, negative 17. So, yeah, so in other words, B minus D is 17. So B has to be bigger than D by 17. So B is going to have to be at least 17. If you make D, even if you make D 0, B is going to have to be 17. So that's the smallest number of students, because D can't be negative. So that's the smallest number of students. And that's probably kind of an overly complicated way of doing this problem. So let me just, I mean, you might see right off that D is going to have to be 0. You're going to have 0 students that, you know, in order to, let's see. Yeah, I guess if you have some students that have neither, that's going to give you even more that have both, right? So if you have, I mean, there's a lot of right-handed students, there's a lot of students with brown hair, so there's going to have to be a lot in the overlap region. Another way to think about it is you could line up the 28 students like this, and you could say all the ones on the right over here are, let's say, right-handed, and we could put all the ones on the left over here could be brown hair, right? Brown hair. And this brown hair is 21, and this right-handed is 24, and there's 28 total. And we'll just make sure that there's nobody that's neither brown hair nor right-handed. And then you just have to take this 28 and you know, subtract. You can find out what this distance is here, right? It'll be the sum of these two minus 28. So that gives you 17 right away. So that might be an easier way to do it. Okay, hopefully I didn't confuse you guys too much on that one. Sorry about that. All right, let's take a look at this one. So this one says a standard die is tossed twice. What is the probability of obtaining exactly 1/5? So here, I think it's important that we think about mutually exclusive events. So we talked about how if two events are mutually exclusive, then you can add the probabilities. So for example, you might be tempted to think, oh, well, there's a 1/6 chance that the first die, or that the first die roll is going to be a 5, and then there's a 1/6 chance that the second die roll is going to be a 5. So maybe I can add those two probabilities, and that will give me a 1/3 chance that one of them will be a 5. There's two problems with that. First of all, these two events are not mutually exclusive. You can get 5 on both die rolls, and so you can't just add the two probabilities. And the other problem with that is that it says that the probability of obtaining exactly 1/5. So you really have to think about kind of this grid of possibilities. You can think about there's the first roll you can think about on the x-axis can be 1, 2, 3, 4, 5, or 6, and the second roll you can think about on the y-axis as being 1, 2, 3, 4, 5, or 6. And so you can just think about this whole grid of possibilities, right? So you can split this up into little boxes like this. And each of these outcomes is equally likely. So let's just pick one as an example. So this square right here, this represents the case where the first roll is a 5 and the second roll is a 3, right? And so you have, altogether you have 36 of these possibilities because it's 6 times 6. There's 6 possibilities for the first roll times 6 possibilities for the second roll. And what you can do is just think about how many of these 36 possibilities, all of which are equally likely, satisfy this condition up here that you get exactly 1, 5. And basically you can think about all these ones here along this row, except you can't count this one because there's 2 5s. So basically that gives you 5 possibilities along this row. And then there's also these possibilities along this column where the first one is a 5, right? So these are all also need to be counted. And there's another 5 there. So we have 5 where the first roll is a 5, but the second roll is not. And then we have another 5 where the second roll is a 5, but the first one is not. So altogether we have 10 out of the 36 outcomes where you have exactly 1, 5. And if you put that as a common fraction, which is what they want, that becomes 5/18. So yeah, that was great. Let's take a look at the next one. So this says Karthik is making a pattern that consists of 3 vertical stripes. Okay. Yeah, this almost sounds like he's making a flag or something like that. A lot of the flags in the world are 3 vertical stripes, right? So you can think of a lot of countries where you have a color here, a color here, and a color here. So he's making a pattern like this. He has a selection of stripes that are red, blue, green, and white. Okay, red, blue, green, and white. And it says, if no 2 adjacent stripes can be the same color, how many different patterns can Karthik make? The patterns red, blue, green, and green, blue, red are considered different. So it's not, so you might think, oh, well, red, blue, green, and you know, if you put those 3 stripes together and made a flag like this, red, blue, green, you could just turn that upside down and it would be green, blue, red. But they're telling us those are different. They're telling us those are different, so we shouldn't consider these the same. Okay, so the way to think about this is it's a little bit like the outfit problem. You know, or maybe a little bit like putting the hats on a shelf. So you can think about each one of these stripes, how many possibilities there are. So for this first leftmost stripe here, how many different possibilities are there? Well, there's 4 because he's got 4 different colors, red, blue, green, white. So let's say there's 4 possibilities there. Once he makes that selection of that color, how many possibilities are there for this next one here, for this middle stripe? Well, it says that no 2 adjacent stripes can be the same color. So whatever color he picked here, he can't pick that same color here, which means he only has 3 to choose from. And then if he goes on to the final one, this rightmost stripe, how many choices is he going to have there? Well, he can pick the same color as the first color, or he can pick one of the 2 colors that haven't been picked yet. He just can't pick this one that's in the middle. So he again has 3 choices. So this is a little different than because it never says all the colors have to be different. You can have the same color on the left and the right. Kind of like there's a flag that's red, white, red, I think. So he could make, I think that's Poland, maybe. You could make the Polish flag. Maybe I'm wrong about that. But anyway, there's some flags that are like that, where you have the 2 sides the same color. And that's a legitimate possibility for him here. So it's 4 times 3 times 3, and that's gonna be 36 if you multiply it out. So there's 36 possibilities, 36 different flags that he can make. All right, let's take a look at the next one. This one says the probability that Chris will win the first set of a tennis match is 2/3. Okay, so 2/3 that he'll win the first one, and that he will win the second is 1/2. Okay, so it's 1/2. So this is the first match, win, and this is the second match, win. Assuming independence of the 2 sets, what is the probability that he will win both sets? Express your answer as a common fraction. Okay, so we learned earlier that if 2 events are independent and you want to know the probability of both of those things happening, then you can just multiply the two probabilities together. So here we just multiply these two together. 2/3 times 1/2 is going to be 1/3, and that's our answer. So that's a pretty simple one, but yeah, maybe I will point out a little bit about independence. So for example, you might think if Chris was the type of person who got discouraged when he lost the first set, and that made him sort of give up or play worse in the second set, then these two probabilities might not be independent. So for example, he might have 2/3 of a chance of winning the first set, but if he won the first set, then he might have more than a half chance because he's feeling good, he's feeling energized, he's maybe he has a 3/4 chance of winning the second set in that case. And maybe if he loses the first set, he gets discouraged and he kind of gives up, and maybe he only has a 1/4 chance of winning in that case. That would be an example of where the two events were dependent on each other. They were not independent. And so you wouldn't be able to multiply the probabilities. I mean, it wouldn't even make sense here. But actually, to figure this out, you would have to say the probability of him winning both would be, in this case, it would be 2/3 times 3/4, because that's the probability that he wins the second if he wins the first. So you would multiply those two together, and you would just kind of ignore this probability. Yeah, okay, so hopefully that made sense. All right, this one says one stamp is randomly selected from a 10 by 10 sheet of 100 stamps. Okay, so you got this sheet of stamps, and there's 10 rows. I'm not going to draw them all. It's 10 columns. It's like a big 10 by 10 grid, right? 10 by 10 grid. And it says, what's the probability that the stamp selected is not along an outer edge? Express your answer as a common fraction. So this one's not too hard, I think. You just have to think about how many of these stamps are not along an outer edge. So you have to take kind of the square in the middle, right? And you have to think, how big is that square? Well, that square is missing one on the left side and one on the right side and one on the top and one on the bottom. So instead of being 10 by 10, it's going to be 8 by 8, which means there are 64 of these stamps that are in the middle that are not along an outer edge. So what is the probability that the stamp selected is one of these 64? Well, it's just going to be 64 divided by 100, which is, if we divide top and bottom by 4, we get 16/25 in order to get it as a common fraction. So that's the answer there. All right, let's go into the next one. This one says 2 points are randomly placed on a number line from -1 to 1. So here's 0, here's 1, here's -1, and you're going to put 2 points randomly somewhere. Maybe one's here and one's here, right? That's one possibility. Maybe one's here and one's here. Could be anything. Maybe one's here and the other one's right next to it. So 2 points are randomly placed on a number line from -1 to 1. What is the probability that the origin lies between the 2 points? Okay, so for example, in the cases that I drew, in the blue case, the origin is between the two. The origin is 0. And in the green case, it's not. And in the orange case, or the gold case, or whatever, it's also not. So I think here, it's useful to think about picking one of the points first. Sometimes that, when they say you pick two things, it can be useful to think about picking one first and then picking the other. So when you pick the first one, it might be on the left side of the origin, it might be on the right side of the origin. I suppose you could argue that it might be exactly on the origin, but that's a probability 0 event. Because if you think about it, there's an infinite number of points you can pick, and there's only one that's exactly at the origin. So the probability of picking exactly on the origin is you can think of it as being like 1 over infinity. Basically, it's a probability 0 that you will get exactly on the origin. So it's either going to be on the left or the right. What's the probability that's going to be on the left? It's going to be a half. There's a half a chance that it's going to be on this side, and there's a half a chance that it's going to be on this side. Now, what about what's going to happen when you pick the second one? Well, the second one is also going to have half a chance of being on the left and half a chance of being on the right. Well, let's just consider the case where where the first one was on the left. So now the second one is going to have half a chance of being on the same side, right? And if it's on the same side, the origin is not going to be between it. So it's also going to have half a chance of being on the opposite side. So the probability, in the case where you pick the first point on the left side, you're going to have half a chance that the origin will be between the 2 points. And the same thing is true if the first was picked on the right. If the first is picked on the right, you still have half a chance. It's just the other half. It's this half. So in either case, you have half a chance. And so the probability is just 1/2. Probability is just 1/2 that you're going to have those 2 points on opposite sides of 0. Okay, well, let's take a look at this one. This says a penny, a nickel, and a dime are tossed simultaneously. What is the probability that exactly 2 of the coins show heads when they land? Okay, so we had a similar one to this before, I guess about 2 out of 4 coins. So this is very similar. It doesn't matter that they say penny, a nickel, and a dime. All we care about is that there are 3 coins. We're going to toss them, and we want to know what the probability is that 2 of them are heads. So this is going to be 3 choose 2. That's the number of ways we can choose 2 of them to be heads, divided by the total number of possibilities, which is 8, which is 2 cubed, right? So this is 3 choose 2 is going to be 3 divided by 8. Or this 8 I got by doing 2 cubed, right? Because there was 2 possibilities for the first coin, 2 possibilities for the second coin, 2 possibilities for the third coin. Just multiply them all together, you get the denominator. That's the total number of possibilities. So the answer here is 3/8. Okay, let's go on to the next one. This one says Manny has 2 red socks. So we got red, red, 2 white socks, white, white, and 2 blue socks, blue, blue. And he plans to choose 2 socks at random to wear today, 2 of the remaining socks to wear tomorrow, and will wear the last 2 remaining socks the next day. What is the probability that on all 3 days Manny wears 2 different colored socks? So in other words, what's the probability that he'll never wear matching socks during those 3 days? And it says express your answer as a common fraction. So I think it's useful to break it down into the 3 days. So let's start with the first day. What's the probability that he's going to wear mismatched socks on the first day? Well, I think it's useful to think about him picking one sock first and then picking the other sock. So the first sock might be red, right? It might be red, it might be white, it might be blue. But whatever it is, let's say it's red, there's going to be a 4/5 chance that he's going to have a mismatched sock, because once he picks that one, of the 5 remaining, 4 of them will be mismatched, right? So if he picks this red one, 4 of the remaining 5 will be mismatched. If you were to pick this white one, 4 of the remaining 5 would be mismatched. So the probability that he's got mismatched socks on the first day is 4/5. Now we have to multiply by the probability that he's going to wear mismatched socks on the second day, given that he wore mismatched socks on the first day. So given that he wore mismatched socks on the first day, what's going to be left? Well, there's going to be 1 sock of one color. For example, it might be red. There's going to be 2 socks of another color. That might be white. And then 1 sock of another color, for example, blue. Now, white might not be the one that has the pair, but it doesn't matter. One of them will have a pair and the other 2 will not, right? And so he's going to pick 2 of these. He might pick these 2, 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 or he might pick these 2, or he might pick these 2. There's 6 possibilities there for the pair of socks that he will pick. And in 2 of those cases, well, yeah, I guess maybe let's think about how many of those cases will it be mismatched. Well, we really got to think about the last 2 days together, I guess, because if he picks any of these 4, I'm going to mark them with a blue dot here, these 4 here, both the second and the third day will be mismatched. So for example, he picks red, white, then this other one will be white, blue. If he picks red, white like this, the other one will be white, blue. If he picks white, blue the first day, then he'll have red, white the second day. And if he picks this white, blue, he'll have red, white. So 4 of the possibilities, 4 out of the 6 possibilities will give mismatched socks on both the second and the third day. But what about if he picks one of the other 2 possibilities? Well, if he picks the white and the white, obviously that's not going to be mismatched on the second day. But even if he picks the red and the blue, then that means he'll be mismatched on the third day. Or, sorry, he'll be mismatched on the second day, but on the third day he'll be matched. So those 2 possibilities don't work. So we just need to multiply 4/5 and 4/6. And 4/6 is the same thing as 2/3. So this is going to be 8 over 15. So that's our answer there. Let's go ahead and move on to this one. This one says Jorge randomly chooses 2 chips from the 6 chips shown without replacement. What is the probability that the sum of the numbers on the 2 chips is greater than 18? Express your answer as a common fraction. Okay, so there's a lot of different pairs of these 6 chips. In fact, there are 6 choose 2 pairs, which is 6 times 5 divided by 2 factorial, which is equal to 15. So there are 15 pairs. If I were to draw them all, like this would be a pair, 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 pair. That's 1, 2, 3, 4, 5, 6, 7 of them, but there's another one there, right? So 8, 9, 10, 11, and then this one. Anyway, there's 15 of them altogether if I were to draw all these guys. Because that's 6 choose 2. So how many of those have the sum greater than 18? So the thing that's useful here is to think about those 2 chips being ordered. So you have the smaller one and then the larger one, and you put them in order. Put them in this order, smaller one then larger one. And then you can think about, okay, what does the larger one have to be? Or what are the possibilities for what the larger one is? And in how many of those cases, for each choice of what the larger one is, what smaller numbers can I pick that will make the sum greater than 18? So let's just start with the biggest large number. The biggest large number is 32. And if I pick 32, I could pick any one of these 5 others in order to have a pair that's greater than 18, because 32 already is greater than 18. So if 32 is the large one, that gives me 5 pairs. 5 pairs where 32 is the larger one. What about if 16 is the largest one of the 2? Well, if 16 is the largest one, the other one could be 1, 2, 4, or 8. And there's only one of those there are 2 of those, 8 and 4, that will sum with 16 to give something bigger than 18, right? Because if you go down to 2, it's going to be equal to 18, which is not what we want. We want something greater than 18. So 16 gives us 2 pairs. And then if you go down to the next largest large number, it would be 8. If 8 is the largest number, there's no way you're going to get above 18, because the other number is even smaller. So the total number of pairs where you get something bigger than 18 is just these 5 plus 2, which is 7. So you got 7 pairs where it's bigger than 18, and then the total number of pairs was 15. So the probability is going to be 7 out of 15. All right, great. Let's move on to this one. So this one says jar A has exactly 4 red buttons and 8 blue buttons. Okay, so this is jar A, and it's got 4 red buttons, and then it's got 8 blue buttons. Okay, and that says Carla removes the same number of red buttons and blue buttons from jar A and places them into the empty jar B. Okay, so this is jar B over here, and it gets X. We don't know the number yet, but it gets X red. It gets X red, and it gets X blue. And then once she does that, now A is going to have, instead of having 4, it's going to have 4 minus X red, and instead of having 8, it's going to have 8 minus X blue. All right, and it says jar A now has 2/3 of its original number of buttons. Okay, so the total number of buttons in jar A is going to be 12 minus 2x. And that's equal to 2/3 of the original number, which was 12. So 2/3 of 12 is just 8. So we can solve for x here. X is 2. Okay, so now we know that there are 2. We can replace x with 2 now. So let's see. Let's do that. So x is 2. So 4 minus x will be 2, and 8 minus x will be 6. Okay, so there are now 2 reds here, 2 reds here, and there are 2 blue here, 6 blue here. Okay, now it says if Carla were now to randomly choose a button from jar A and a button from jar B, what is the probability that the 2 chosen buttons will both be red? Okay, so if she was to choose so these are independent events now. If she chooses one from A and she chooses one from B, we can have the probability that the A is going to be red. That's going to be 2 over 8, because 2 of them are red out of the 8 total. And there's going to be a 2 out of 4 probability that the B one is going to be red, because there's 2 reds out of 4 total. So we multiply those two together. So 2/8 times 2/4, that's going to be 4 over 32, which is simplified to 1 over 8. So that's our answer on that one. Okay. Let's take a look at this one. This one, I think I can show you a nice concept about using geometry to figure out probabilities sometimes. So this says a point xy is randomly selected such that x is between 0 and 8 and y is between 0 and 4. So we can draw like a coordinate axis here, and we can put 8 here and 4 here, because x has got to be less than 8, and y has got to be less than 4. Between 4 and 0, and x is between 8 and 0. So this is the sort of rectangle of valid xy points. Any point inside this rectangle has height of 4 and width of 8. Any point inside that rectangle is a valid point that we could pick. And then it says, what's the probability that x plus y is less than or equal to 4? So what part of this rectangle is x plus y going to be less than or equal to 4? Well, we can just graph y equals 4 minus x. Or y, sorry, I should say y less than or equal to 4 minus x. So the line where y is equal to 4 minus x will start here at this point and will go down to this point. So the area where y is less than that is going to be, let me put it in a different color here. So it's going to be this area down here, right? This triangular area in here. And so we want to know the probability. If you pick a random point in this rectangle, what's the probability that's going to be in this triangle? And for that, we can just use the area of the triangle divided by the area of the rectangle. So the area of the triangle is going to be 1/2 the base times the height, and the area of the rectangle is just going to be the width times the height of the rectangle. So this is the height of the triangle, base of the triangle, height of the rectangle, width of the rectangle. So this is going to be 1/2 of 4 times 4 is 8, and 4 times 8 is going to be like this. We can cancel the 8s and we just get 1/4. You can kind of see that triangle is 1/4 the area by maybe chopping this. It's equal to this triangle and this triangle and this triangle, so it's 1/4 of the area. That's our answer there. All right, let's take a look at this one. This one says 7 sticks with length 2, 3, 5, 7, 11, 13, and 17 are placed in a box. Okay, 2, 3, 5, 7, 11, 13, and 17. Those are the lengths of the sticks that we put in our box. 3 of the sticks are randomly selected. What is the probability that a triangle can be formed by joining the endpoints of the sticks? Okay. Express your answer as a common fraction. So, can I always make a triangle if I have 3 sticks by forming their endpoints together? Well, if you think about that a little bit, you'll realize that the answer is no. And the reason is, if you look at the longest stick, it might be longer than the other 2 sticks put together. So let's say you had 17 here, just as an example, and then you picked 2 and 3, right? Those 2 and 3 would only in total add up to 5, and they would never be able to reach from one endpoint of this 17 stick all the way. 17 is pretty long compared to 2 or 3, all the way to the other endpoint over here. All right, so basically, in this problem, it's going to be useful to again order the 3 numbers that we pick and consider what the largest one is. So there are several possibilities for what the largest of the 3 sticks are. The largest one could be 5 if you did 2, 3, and 5. It could be 7, it could be 11, it could be 13, and it could be 17. Any one of these could be the largest of our 3 sticks. You can't have 3 or 2 be the largest because they're the 2 smallest ones. So let's just take each one of those cases separately and see how many times we can get a triangle where the 2 smaller numbers are at least as big as the largest. Let's start with 17. So if 17 is our largest, then what pairs of these other numbers could add up to give me something that's bigger than 17? Well, let's think about what my next biggest number is. If my next biggest number is, let's put the largest here, and then we'll put the medium one here. The medium one could be 13, or it could be 11, or it could be 7, and so on. If the medium one is 7 or smaller, you're not going to be able to get something that adds up to 17, so we don't need to consider that one. If it's 11, there's only one possibility. Basically, if it's 11, you're going to have 7, because all these other numbers that are lower than 7, they're not going to add up with 11 to be something as big as that's bigger than 17. They need to add up to 18 or bigger, and the only one that'll do it is 7. And then if it's 13, you're going to need at least 5. So the smallest number can be either 5 or 7. So basically, with the largest one being 17, there are 2 possibilities here, and there's 1 possibility here. So altogether, there are 3 possibilities. So let's put a 3 there. If the largest one is 17, there are 3 possibilities. What about if, let's make some room. Let's say, what about if I'm going to just erase this. What about if the largest one is 13? So the largest one is 13, then the medium one could be 11, or it could be 7. But I'm realizing right away that if it's 7 or smaller, you're never going to be able to add up to something bigger than 13, because even 7 plus 5 is only 12, so we don't need to consider this case. If it's 11, I could have 3 for the smallest. I could have 3, or I could have 5, or I could have 7. Those all will add up to something that's bigger than 13 when combined with 11. So there are 3 possibilities there. So let's put 3 here. Now let's go down to the case where 11 is the largest. So this is really just a matter of a bunch of different cases. So if the largest, the medium, the small, if the largest is 11, I'm going to have to add up to 12 at least, and the only way to do that is 5 and 7, so there's 1 possibility. If the largest is now 7, I'm going to have to add up to at least 8, which I can do with 3 and 5, but no other possibility, so that's another 1 possibility there. And then if the largest is 5, I have to add up to at least 6, which I can't do with 2 and 3, so that doesn't work. So I'm all done. I basically have this many ways to make a triangle. So 3 plus 3 plus 1 plus 1, that's 8 ways to make a triangle. And in order to turn that into a probability, I need to divide by the total number of ways that I can pick 3 sticks out of this box. So how many ways can I pick 3 sticks out of a box? Well, that's just 7 choose 3, 7 choose 3, or in other words, you can write it as 7 choose 3, which is equal to 7 times 5 times 4 divided by 3 times 2 times 1, because this is 7 factorial divided by 4 factorial, and then also divided by 3 factorial. So this gives me 2. Oh, whoops, I did that wrong. One sec, I forgot 6. It should be 7 times 6 times 5 divided by 3 times 2 times 1. My mistake. And this is just 6, so it cancels with that, and you get 35. So that'll be the denominator here. There's 35 total ways to pick 3, and only in 8 of those can we form a triangle. So the answer, did I do that right? I think I might have missed one. Let's see. I think I missed one. I think I messed up at some point there. Let's try that again, because this is different than the answer I got before when I did this. So let's consider the case of 17 again. 17, 17, you have 17 and 13. You can use 11 or 7 or 5. So this can be 11 or 7 or 5. So that's 3 possibilities there. So this is large, medium, small. And then if you had 17 and 11, you could have a 7 here. So yeah, there are 4 possibilities altogether, 3 here and 1 here. Somehow I messed this up. I apologize for that, but this one is supposed to be a 4 instead of a 3. So now if I do 4 plus 3 plus 1 plus 1, that's actually 9 over 35. So that's going to be my final answer. I must have messed up. You guys have probably all noticed it when you were watching it earlier. So that, anyway, I apologize for that. Okay, this one says Heather places 5 red balls and 5 green balls in any combination into 2 identical boxes. A box is randomly selected and then a ball is randomly selected from that box. Heather wins if a green ball is drawn. One particular distribution of the balls between the boxes will maximize Heather's chances of winning. What is the probability that Heather will win if she uses the distribution that maximizes her chances? Express your answer as a common fraction. Okay, this is a really complicated problem, but you've got these 2 boxes, and you've got 10 balls, and 5 of them are red, right? So you've got 5 red balls, and then you've got 5 green balls, right? You've got 5 green balls, and you can put these balls, each ball you can choose to put in this bin or this bin. So if you want, you can put all the balls in one bin, or you could put 5 balls in one and 5 in the other. Like you could put all the red in one and all the green in the other. I guess you don't, yeah, so we could think about that. Like there's so many different possibilities for how to arrange them, right? But you're not going to pick a random ball. You're going to pick a random box, and then you're going to pick a random ball from that box. So if we were, for example, to put the same number in each bin, then it wouldn't matter how we distributed them because each ball would have the same likelihood of getting chosen. If we put more balls, let's say we put more balls in here and fewer balls over here. Now these balls have a higher probability overall of getting chosen than these ones over here. And so it's probably a good idea to put red balls over here, right? Only red balls, because these are the ones that are going to be more likely to be chosen. So, the question is, how many red balls do we do? We could put 1 red ball over here. If we did that, then we would have the other 4 red balls over here, and we would have all 5 green balls over here. That's one possibility. Or we could put, more than 1. So I'm just going to draw a line. That's one possibility up above there. But another possibility would be to do 2 or 3 or 4 or 5. And that would reduce the number of red balls over here. And we can think about maybe we can think about these two possibilities and see which trend is better. So in both cases, you have a half a chance of picking this box. And it doesn't matter whether there's one ball or two balls in there. You're going to have, once you pick this box, you're going to have a 100% chance of picking a red ball. But over here, you're going to have a different probability of getting red depending on the number of red balls in here. So you know, putting more red balls over here is only going to decrease your chance of getting red if we choose this box. So this is not as good. And going even further, putting more red balls in here is also not going to be good. So this is the best she can do, is to put just one red ball over here and all the other 9 balls here. And then now that we figured that out, we can look at the final question here. It says, what's the probability that Heather will win if she uses this distribution? So the probability that she's going to win, she wins by choosing a red ball, right? Let's see, Heather wins. She wins with the green ball. Okay, swap everything I did so far. Okay, let's fix it. So she wants one green ball. I'm sorry. She wants one green ball over here. And then she wants the 5 red balls over here. And then only 4 green balls over here. So she wins if she gets a green ball. So she's going to have a half a chance of choosing this box, and she's going to have half a chance of getting that box, and if she chooses that box, the probability is 1 that she'll get the green ball. And then she's going to have a half a chance of getting the other box, and if she does that, she'll have a 4/9 chance of getting the green ball. So you multiply 1/2 times 1, that gives you 1/2, and then you add 1/2 times 4/9, that'll give you 4/18. And if we add these together, this will be 9/18 plus 4/18. That'll give you a total of 13/18. So that, I believe, is the answer there. Okay, great. Let's take a look at the next one. This one says, Thomas, Carrie, and Lenny each captain a different one of 3 hockey teams. Each captain will choose 4 players from a pool of 12 players, with each player chosen for only one team. How many different ways can the teams be formed? So this is the first really complicated one, I think. And in this one, there's a couple different ways to do it. And I want to show you 2 different ways. One is you could think, okay, you got 12 players, you're going to choose 4 for Thomas's team. So the number of ways you can do that is 12 choose 4. And then once you've done that, there's 8 players left, and you're going to choose 4 of those for Carrie's team. And then once you've done that, there's 4 players left, and they're all going to be chosen for Lenny's team. So that's 4 choose 4, which is just 1. But we would need to multiply these 3 together to get the total number of ways to choose the 3 teams. So what is this going to be? This is going to be 12 factorial over 8 factorial 4 factorial times 8 factorial over 4 factorial 4 factorial times 4 factorial over 4 factorial 0 factorial. Okay, so this 4 factorial cancels with this 4 factorial, 0 factorial is just 1. This 8 factorial cancels with this 8 factorial. And now we just have 12 factorial over 3 different 4 factorials. So this is going to be 12 times 8, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5, and then there's going to be times 4 all the way down, but I'm going to cancel that with one of these 4 factorials. And then all that's left is another 4 factorial here and another 4 factorial here. These are each 24, so maybe I'll just do 24 times 24 down on the bottom. 24 times 24. And I can start canceling things. This gives me 3. I can cancel this to give me 2. I can cancel this to give me 2. I can cancel this to give me 5. And now what's left? I have 11 times 5 times 9 times 7 times 2 times 5. These multiply to give me 70. These multiply to give me 55. well, what's the best way to do this? Yeah, 55. And then 9 times 70, that's going to be 630. So it's 630 times 55. So it's a little bit of a pain, but anyway, you can do 63 times 55 times 10. So it's going to be 15, 31, and then let's see, 15. Yeah, it's going to be the same thing. 31. So this is going to be 5, 6, 4, 3, and then I had to multiply by 10. So altogether I've got 3, 4, 6, 5, 0. And that's my final answer. So that's the answer to that one. So that was kind of a lot of work. There's another way to do this. You could think of this as yeah, you can think of this a little bit like the number of ways to arrange letters. So let me show you. Let's see if I can show you how that works. So imagine you have your 12 players that need to get split up into the 3 teams, right? Oops. Let's see, let me fix that. You have your 12 players that need to get split up into the 3 teams. And let's see. Let's say that's player 1, 2, 3, 4, 5, 6, all the way up to 12, way over here. And then let's say that I had a word that had 4 T's, so 4 C's and 4 L's, right? So I could do TCL, TCL, T, T, L, L, L. Oops, I got 5 L's. L, L, C, C. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've got 4 of each, right? Yeah. So if I made a word, you could ask the question, how many different words, how many different ways can I orient, how many different ways can I order these 12 letters? 4 of them are T's, 4 of them are C's, and 4 of them are L's. And then what you would do is you would say, okay, with this ordering, player 1 would be on Thomas's team. Player 1 would be on Thomas's team. Player 2 would go on to Carrie's team. Player 3 would go on to Lenny's team. Player 4 would be Thomas's team again. So any way you can order these 12 letters would represent one way that they can split up their teams, right? So then we can just use our trick of how many different ways there are to arrange letters. And that is just the number of letters, factorial, that's 12 factorial, divided by, since there are 4 identical T's, we have to divide by 4 factorial for that. And then since there are 4 identical C's, we have to divide by another 4 factorial there. And then since there are 4 identical, whichever one I didn't say, L, they divide by another 4 factorial there. And so that gives you the same result. We had this at one point in the other derivation, and when we did all the canceling and multiplied it all out, we got our answer, which was 34650. So, okay, I've just got a couple more to go. Let's take a look at this one. So this says Cami made a list of every possible distinct 5-digit positive even integer that can be formed using each of the digits 1, 3, 4, 5, and 9 exactly once in each integer. Or each once, yeah, exactly once in each integer. What is the sum of the integers on Cami's list? Okay, so she's got these 5 digits, 1, 3, 4, 5, and 9. And the first thing that we have to think about is how many, when you arrange these, we need it to be an even integer. And the only way for it to be an even integer is if we take the 4 and stick it at the end. So we have no choice on which digit goes last. But we have 4 spots in front of the 4 that we can choose however we want. It doesn't matter how we arrange the 1, the 3, the 5, and the 9. It's always still going to be an even number as long as we have the 4 at the end. So how many of these integers are there going to be? Well, there's going to be 4 factorial of these things because it's the number of ways we can arrange these 4 unique digits in these 4 spots. 4 factorial is 24. And then another thing that's important to realize with this is that each digit is going to show up the same number of times in the tens place. Each digit is going to show up the same number of times in the hundreds place, the thousands place, and the 10,000s place. So if that's the case, you're going to have 6 ones, 6 threes, 6 fives, and 6 nines in the tens place. So the total number of tens you're going to have, if you add them all up, is going to be 6 times 1 plus 3 plus 5 plus 9. Because that's 1/4 of the 24, right? So 1/4 of them are going to be ones, 1/4 of them are going to be threes, 1/4 of them are going to be fives, 1/4 of them are going to be nines. So 1/4 of them is 6, so we can just do 6 times this sum. This sum is 15. So so 15 times 6 is going to be 90. Wait, hold on. Did I add that wrong? This is not right. This is 18. This is 18. So 18 times 6 is going to be 108. Is that right? 18 times 6. Yeah, that's going to be 108. And so there's going to be, basically, once I add those all up, there's going to be 108 tens. There's going to be 108 in the hundreds place. I mean, we can't put 108 in those places, but we can add it up like this, like 108 in the tens thousands place, plus 108 in the thousands place, plus 108 in that place, and 108 in the tens place. And then what's going to be in the ones place? Well, it's going to be 4 all the time. So 4 times 24, that'll be 96, right? So we just add 96. So we're just going to add these all together. See, the 108 tens is going to be 1080. The 108 hundreds is going to be 10,800. The 108 thousands is going to be 108,000. And the 108 10,000s is going to be 1,080,000. So we're just going to add these all up. We're going to get 6, 7, carry the 1. You're going to get 9. Here you're going to get 9. Here you're going to get 9. And then you're going to get 1 and 1. So this is our final answer. It is 1,199,976. Okay, hope you guys enjoyed that one. This one says Jeff will pick a card at random from 10 cards numbered 1 through 10. The number on this card will indicate his starting point on the number line shown below. He will then spin the fair spinner shown below, which has 3 congruent sectors, and follow the instructions indicated by his spin. From this new point, he will spin the spinner again and follow the resulting instruction. What is the probability that he ends up at a multiple of 3 on the number line? Express your answer as a common fraction. Okay, so he's going to start at a random spot on this number line, except it has to be between 1 and 10. That'll give him room to move up to 2 spaces in any direction. So he's going to start at one of those spots, one of these spots from 1 to 10, some random spot from 1 to 10. And then he's going to spin the spinner, and the spinner is either going to say to go right or to go left. In fact, 2/3 of the time it's going to say to go right. So this one and this one both say right, and then this other one says to go left. So 2/3 of a chance is he's going to go right, and 1/3 of the chance is he's going to go left. And the question is, after he does that 2 times, what's the probability that that he ends up at a multiple of 3? So I think what's useful to do here is to say, think about the probability after 0 moves. So after 0 moves, in other words, right after he picks his random number from 1 to 10, and then after 1 move, and then after 2 moves, right? So this is the number of moves that he's done. What we really care about is what's going to happen after 2 moves, but I think it's going to be easier to do this one step at a time, where we start with just after 0 moves. So there's some probability that he's a multiple of 3, and I'm going to actually compute 3 different probabilities. The probability that he's a multiple of 3, so that's going to be like a 3n type number, where n is an integer, or he might be like a 3n plus 1, meaning that he's 1 more than a multiple of 3, or he might be at a 3n plus 2. Every number is either a multiple of 3, or 1 more than a multiple of 3, or 2 more than a multiple of 3. So after 0 moves, what's the probability there's going to be a multiple of 3? Well, that's just going to be 3/10. Because 3 of these numbers from 1 to 10, specifically the 3, the 6, and the 9, are going to be multiples of 3. So the probability here is 3/10. The probability that he's going to be 1 more than a multiple of 3 is 4/10, because we have 4 numbers that are a multiple of 3 plus 1. Specifically, we've got 1, we've got 4, we've got 7, and we've got 10. And then the probability of being 3n plus 2 is just whatever's left. We already took 7 of the spots, so there's 3 more, so it's 3/10 chance that he's going to be 2 more. And now what happens is, in each of these cases, you've got, so for example, let's take the 3n plus 1 case. You're going to spin the spinner, and 2/3 of the time that you're here, you're going to go over to here. So that's going to happen 2/3 of the time. And 1/3 of the time, you're going to go over to here, 1/3. And then the same thing is going to happen with this one. 2/3 of the time, it's going to wrap around to here. And then 1/3 of the time, it's going to go back this way. And then this one, 2/3 of the time, it's going to go this way. And 1/3 of the time, it's going to wrap around to go over here. So we can compute the probability that, we can compute these 3 probabilities here by combining those. So for example, this one here will be, let me write it in a different color maybe, oops. This will be 2/3 of the 4/10 plus 1/3 of the 3/10. And so it's going to be some number of 30ths, right? It'll be 8 plus 3, that'll be 11/30ths. So let me just erase this and replace it with 11/30ths. Okay. So this is 11/30ths. And then this one is also going to be some number of 30ths. It'll be, there's two, let's see, there's, did I do that right? Yeah, so this one is going to have, well, it's going to be 2/3 of 3/10 plus 1/3 of 3/10. That's just going to be 3/10, right? That's just going to be 3/10. And then this one will have 2/3 of 4/10. I did this one wrong. This was supposed to be 1/3 of 4/10, 2/3 of 3/10. So 1 times 4 plus 2 times 3, that's 10. Wait. 2, 1, that's 4 plus 9. Oh no, that's right. 4 plus 9. No, 4 plus 8. 1 sec. Oh yeah, this is going to be 2/3 of 3/10. So that's going to be 6/30ths. Plus 1/3 of 4/10. That's going to be 10/30ths. That's 10/30ths. Something's not right there. 2 times 3. 2/3. Yeah, that's right. 2/3 of this plus 1/3 of this is going to be 10/30th. So that's going to be 1/3. Okay, so that's just a third. 1/3. And then this one will be 2/3 of 4/10, which is 8/30ths plus 1/3 3/10, which is 3/30ths. So that's the one that's 11/30. And if we add these up, they should be 1, right? So how many 30ths do we have? 11 plus 9 is 20 plus 10, yeah. So that's right. And then we do that all one more time. So here we take 2/3 of this one. So it's 2/3 times 1/3 plus 1/3 times 11/30ths. So that's going to be some number of 90ths, right? So this is 11 90ths plus 20 90ths. That's going to be 31 90ths. Actually, we don't even need to compute this one. Yeah, let's not even worry about this one because we don't care about this. The question asks specifically just about this one here. So we just need to do 2/3 of 11 30ths plus 1/3 of 3/10. So let's see, this is going to be 22 90ths plus this one's going to be 9 90ths. So that is going to equal 31 over 90. 31 over 90. That's our final answer there. That one was on a national, that was problem 28 on a national sprint in 2004, so it was a pretty tough problem. All right, we got 3 more to go. 3 more to go. If you're stuck with it this far, you're amazing. Amazing. All right, Kai has 100 identical blue rods, each of length 3 inches, and 100 identical white rods, each of length 1 inch. In how many ways can Kai arrange these rods in order from left to right to form a row that is exactly 10 inches in length? Here is one such arrangement to include. So you have a 3-inch blue, then a 1-inch white, then 2 3-inch blues. So this is what we call casework. You have to think about, you have to break it down into a few different cases, and the nicest way to break this down is based on how many blues you have. So you could have 0 blues, you could have 1 blue, you could have 2 blues, or you can have 3 blues. You can't have any more than that because 4 blues is already 12 inches. So these are our 4 cases that we need to think about. If you have 0 blues, that means you have all white. So there's just going to be 10 whites next to each other. So that's just, there's only going to be one possibility there. So we can just put a 1. That's just going to give us one possibility, 10 whites. It's going to be 10 whites. And then if there's 1 blue, the total number of rods is going to be 8 because we're going to have 7 whites and 1 blue. So out of those 8, we have to choose one of them to be the blue if we put them in order. So for example, we could do blue and then 7 whites. 1, 2, 3, 4, 5, 6, 7. Or we could do a bunch of whites first. 1, 2, 3, 4, 5. And then we could do the blue and then another white. Or, yeah, how many did I get? 1, 2, 3. 1, 2, 3, 4, 5, 6. Oh, there's another white. So maybe put that here. So basically the blue can be, any one of these 8 can be the blue. So this is 8 choose 1, which is just going to be equal to 8. And then for the case where we have 2 blues, we're going to have a total of 6 rods because we're going to have 5 white. Is that right? Hang on. No. Did I do that right? There's, oh, not 5 white. There's going to be 4 white. 4 white and 2 blue. That's a total of 6, right? That'll be, the 4 whites will be 4 inches, and then the 2 blue together will be 6 inches. That'll give us 10 total. So it's 6, and we need to choose 2 of them to be blue. So that's 6 choose 2, which is 6 times 5 divided by 2 factorial, which is just 15. And then the case where there's 3 blue, that's this case here, we have 3 blue and 1 white for a total of 4. So we have 4, and we're choosing one of them to be blue, so that's just going to be 4. So altogether we have 1 plus 8 plus 15 plus 4, and we just add those together. 12 plus 16 is 28 different ways. So that's that one. We've only got 2 left. These 2 are pretty tricky. This one says Jalen has a wooden cube which is painted blue on the outside. She cuts the cube into 1,000 identical cubes, some of which have some sides painted blue, then rolls the resulting cubes like dice. The probability that no blue faces land up after Jalen rolls the 1,000 cubes can be expressed as 2 to the a. So 2 to the A times 3 to the B times 5 to the C, where A, B, and C are integers, and they want to know the value of A plus B plus C. This is a really tricky one. So you've got this big cube that's painted blue. Maybe I should draw it in blue. Got this big cube that's painted blue. And then you chop it up into 1,000 cubes. You slice it into 10 slices this way, and then you slice it into 10 slices this way, and then you slice it into 10 slices this way. And when you do that, you end up with 1,000 cubes, right? 1,000 little tiny cubes. And some of them have some blue on them because they were on the outside. They were cubes on the outside, right? And we can figure out how many of them had blue on them. So, for example, there will be some on the top face that are not on the edges. That'll be an 8 by 8 block that just have one of their 6 faces painted blue. So, and then there will be the same thing on each face. So altogether there will be 8 times 8 times 6 that have one face painted blue. Those are the ones on the faces. And then there will be some that are on the corners, and then there will be some that are on the edges. So the ones that are on the edges, there are 12 edges, and there are 8. So we've got 8 times 12 that are on the edges, and they'll have 2 faces blue. And then there will be 8 corner pieces, right? 1, 2, 3, 4 on top, and 1, 2, 3, and then the hidden one back there, 4 on the bottom. So there are 8 corner pieces, 8 of those that have 3 faces blue. Okay, so now we got to figure out this incredibly tiny probability. Well, we don't actually have to find the probability. We just have to figure out what these exponents are. So let's do that. So first, you can think about there's going to be like 8. There's also going to be 8 cubed little cubes in the middle, right? 8 cubed faces that have 0 faces blue. We could think about rolling those ones first. All those ones, none of them are going to show any blue. So the probability is 1 that those will not show blue. And what we want to know is the probability that no blue faces land up. So for those ones, the probability is just 1. But then for these ones, there's these 64 times 6 ones with 1 blue face. For each one of those, the probability of not seeing a blue face land up is 5 out of 6, because 5 out of the 6 faces are not blue. And then if you have 2 of those that you roll, it's going to be 5 out of 6 squared, the probability that you don't see any blue. And if you have 3 of them that you roll, it's going to be 5 out of 6 cubed. But if you have 8 times 8 times 6 of them, your exponent here is going to be 8 times 8 times 6. So this is a very, very, very tiny probability that none of them are going to show any blue. Extremely small. It's 5/6 to this giant exponent power. Then we have to multiply that by another tiny number, which is the probability that none of these guys show blue. So that, since these guys have 2 faces that are blue, they have a 4/6, which is 2/3 probability of not showing blue. And we have to raise that to the 8 times 12 power. And then we have these 8 guys here. They have 3 faces blue, so they have a 1/2 chance. Each of them has a 1/2 chance of not showing blue. You have to take that to the 8th power. Okay, so let's make some room. We have to multiply. Oh yeah, maybe I should do that. We have to multiply these 3 extremely tiny numbers together and figure out what these exponents are. So first of all, this 5/6, we can think of this as 5 over 2 times 3 to this big giant power. So this is going to be equal to 5 to the 8 times 8 times 6 times 2 to the minus 8 times 8 times 6 times 3 to the minus 8 times 8 times 6. So if we were just trying to figure out the sum of a, b, and c just for this part, it would be this sum a plus b plus c would be 8 times 8 times 6 minus 8 times 8 times 6 minus another 8 times 8 times 6. So we can cancel out this one, and it would just be minus 8 times 8 times 6. So let's put that for this one. It's minus 8 times 8 times 6. And then for the next one, we have 2/3 to the 8 times 12. Well, this is going to be 2 to the 8 times 12 times 3 to the minus 8 times 12. So this is, when you do the sum of the exponents here, it's just going to be 0 because you have some positives and negatives and they all cancel out. So this one's just going to be 0. So this is the a plus b plus c coming from this one. This is the a plus b plus c coming from this one. And then you have 1/2 to the 8th, which is going to be 2 to the minus 8. So the a plus b plus c from that one is minus 8. Okay. So basically, if we do this all together, we have minus, let's see. So what's 8 times 8 times 6? That's 64 times 6. 4, carry the 2, it's going to be 384. 384. So this is negative 384, and this is negative 8, and you add those together and you get negative 392. So that is our final answer, negative 392. Okay, we're on the last problem. This one says Kurt is creating a bouquet of flowers for his mother. He has a selection of roses, lilies, orchids, and violets. Okay, roses, lilies, orchids, and violets, from which to create a bouquet of a dozen flowers. Kurt's mother loves orchids, so his bouquet will have at least 6 orchids. How many different groups of a dozen flowers can Kurt use to make a bouquet? So the first thing to do is simplify the problem by noticing that he has to pick at least 6 orchids. Okay, so you can just sort of set those aside. You can say, okay, let's pick 6 orchids. We got 6 orchids over here. Those are just, maybe I should write that out because it looks like a 60. 6 orchids. You pick those 6 orchids, you set them aside. They're going to be part of the bouquet. Okay? And now you need to pick 6 more flowers, and you can choose from any combination of these 4 flowers: roses, lilies, orchids, and violets. So this is a little bit like the problem of distributing 6 pencils to, I had 7 pencils to 4 friends, right? This is distributing 6 flowers to these 4 types, right? So we can do stars and bars. We're going to have 6 stars. 1, 2, 3, 4, 5, 6. And how many bars? We need a bar for each separator between these. So we're going to have 3 bars. 1, 2, 3. And then any ordering of this is going to represent some number of roses, some number of lilies, some number of orchids, and some number of violets that add up to 6. So how many do we have altogether? We have 9. So we have 9 factorial divided by the number of stars, which is 6 factorial, and the number of bars, which is 3 factorial. So this is going to be 9 times 8 times 7 divided by 3 times 2 times 1. This cancels to give us 3. This cancels to give us 4. So we have 3 times 4 times 7, which is 12 times 7, which is 84. And that is our answer, 84. Okay, hope you guys enjoyed that. I know this is a huge video, extremely long, but hey, if you stayed to the end, you're amazing, and I hope you guys learned a lot. Thanks, bye.